question. You have been asked to design a 1 liter oil can shaped like a right circular cylinder. What dimension was used to lease the material? Let's just get right into it. And I'm sorry, guys. Okay, right circular cylinder. Why did it say right circular cylinder? Well, it's just a cylinder, guys. So here it is. I'm just reading the same thing. And I know a little while ago I said, quote unquote, they were LOLing because we did a second take and we said that there was no restriction, but there is a restriction. What's my volume of this? 1 liter. It says right here, 1 liter oil can. Volume. So I have a circle on the bottom and then I add depth. So pi r squared times h. And then I know that I have 1 liter. So what makes this question hard is my surface area. That's what I want to minimize. What dimensions will use the least material? So I want to minimize surface area. I want to minimize surface area. And the issue with that is that surface area is in square centimeters and my volume is in liters. So how am I going to relate liters to centimeters? That's what makes this hard. So do you know how many cubic centimeters are in 1 liter? Okay. So here we go. Now we're talking. All right, guys, you're about to go to a university and you're going to have international students. And I'm not talking smack, but they're probably going to know the metric system. And they're probably going to know how many cubic centimeters are in a liter. So you want to make sure that you know just as much, if not more, than everyone else, right? Or we should at least know as much as everyone. So 1 liter is 1,000 cubic centimeters. You guys never used that conversion somewhere in chemistry? Never? Well, you at least did like molar conversions and did molarity. Did you guys do pH? Like, what's the pH? Okay, so did you guys do redox reactions, alpha and beta? Okay. Well, yeah. So make sure, especially if you're going into STEM, you guys will tell me when you guys swing back, tell me how you did in chemistry compared to your next calculus class or whatever. All right, so this is what makes everything work here. So I'm going to say 1,000 cubic centimeters equals pi r squared h. Are we still okay? Okay. Here's what we want to minimize. See how it says minimize surface area? All right, area. So this right circular cylinder has a top and a bottom. What's area of a circle? Pi r squared. And I have 2 of them, so put a 2 in the front. From the 2 circles, I guess I'll put here for good notes, top and bottom. Plus, and then the wall of the cylinder. It's gonna, because it's a rectangle. Do you guys see that? So I'm gonna put wall is a rectangle. So length times width. So the length is whatever goes around this circle. So that is called what for the circle? In reference to the circle. Shab, I don't understand the question. If I want to know the distance around a circle, what is that called? Circumference. How do I find circumference of a circle?
Radius 2r.
You're close. You're so close. 2
r squared.
No. 2 no. There is, yeah. Oh, okay. What? 2 pi r. Guys, when we were in pre-cal, also in geometry, when I did 1 revolution, we said that was 2 pi radians. Oh, look, circumference, 2 pi r. There it is. That's where the radians came from. Yes. All right. So the wall is a rectangle. So let me go ahead and draw this rectangle here. So this length is 2 pi r, and then the height is just h. See? So 2 pi r times h. That will give you, does that make sense? Okay. So this is your wall. This is wall. Are we okay so far? All right. Well, there it is, guys. This is what we want to minimize. So this is what we're going to take derivative of. The issue is that we have an r and an h, and I don't want to have an r and an h. So I take what I said earlier that we did not have a restriction equation here. And we're going to get this in terms of just r. So get it by h by itself so I can replace it. Does that make sense? Okay, so here we go. I'm going to go, what am I going to do? I'm going to come over here. I'm going to say 1,000 equals pi r squared h. I'm going to divide by pi r squared. You okay? Oh. By a fly? That's a fly. Can't do anything to you. Oh, wow. You did a good impersonation. So there it is. 1,000 divided by pi r squared. I'm going to substitute this dude in here for h. So now I have area equals 2 pi r squared plus 2 pi r, open parenthesis, 1,000 over pi r squared, close it. So I'm just doing a little bit of algebra here. 2 pi r squared plus one of these pi's cancels out and one of these r's cancel out. So I have 2,000 over r. Are we still okay? Okay, here we go. I'm going to take a derivative. So I'm going to write a prime, and I'm taking a derivative with respect to r here. So 4 pi r. And then remember, this 2,000 over r, that's the same thing as 2,000 r to the negative 1. So minus 2,000 r to the negative 2. So let's make it pretty. 4 pi r minus 2,000 over r squared. And since that's my derivative, I'm going to equal this to 0. And let's solve for r. So let's see. 4 pi r equals, I'm going to move this to the right, 2,000 over r squared. I'm going to multiply the right side by r squared, and then whatever I do to one side, I do to the other. 4 pi r cubed equals 2,000. We still okay, guys? All right, divide by 4 pi. So semicolon, I'm going to come right here. R cubed equals 500 over pi. 4 goes into 25 times, so 500. And then I'm just going to do the what? Cube root, cube root, cube root. And I'll figure out what that is in a little bit. R equals the cube root of 500 over pi. That's actually the perfect answer, which is, I'm going to take my calculator. Where's my calculator? Did I never open it? Never opened it. There you go. Math number 4. You don't need number 4. You could just always do it without that. I like to have this little thing here like that. 500 over pi. And I'm going to push enter. And there it is, 5.4192. And I want to store that because I want to start using these little letters here. Guess what letter I'm going to use? No, well, okay, let's use A. I always say go by the alphabet, but in this time, I was going to say R because it's a radius. But I decided to use A. You're right, because I always go by the alphabet. So what's that? What's that number? Yeah. There it is. And Chav, how do I know that's a min? Well, my A prime does change. The lowest you can go is 0. And I'm going to call that, I'm just going to put A to make it clean. Oh, you know what? See, I don't like the fact that A prime and A. That's why I didn't want to use A. That's why. That's fine. You know what? I'm going to change that A to an R. Because I don't want you guys to look at your notes later on and be like, you know what I mean? Like, why does that say A prime when you wrote A there? So change that to an R. And I'm going to change this to an R. Alpha R. Store. Did they go to what?
What's the highest value you can go to?
What do you mean?
A prime, what's the highest value?
Like, how many digits did this store? This goes to.
You said the lowest value was 6.
You said the lowest was 0.
Oh, yeah. It goes on forever.
So that's why you didn't put it.
Yeah, because this is, remember what this, Chop, what is this? Remember what we're doing. This is R. That's the radius. So you're literally giving me the biggest radius I can have. Do you know what I mean? If you can't have a radius of 0, so maybe I shouldn't even put a bracket, because if you have a radius of 0, that means you have no can. So maybe I should be doing like this. There's no foul. Relax, you're fine. There's no foul. No one's gonna be like, oh, this person doesn't know calculus because they put a bracket. You know, they're not gonna say that. At least I hope not, because that would be pretty rude. But this right here, this number is 5.41926. 926. And it does change from negative to positive there. Do you guys want me to just use Desmos so we can see it better? Because Desmos, the graph is a little better. So here it is, guys. Let me type it in Desmos. Desmos does derivatives pretty cool. Did you guys know that? Yeah, check it out. I'm going to call it f of x. That way I can call it f prime. Give me the original area formula.
2 pi r squared.
2 pi. So I'm going to call it x squared. Plus
2 pi r.
2 pi.
2 pi times radius times height.
Yeah, but I want it in terms of x. So just give me this one right here. 2 pi. Where are you? 2,000 over x. 2,000 over x. Right? Oh, I said Desmos. 2,000 over x. Like that. That's my original area formula. So check it out. I can just go here and I can go f prime of x. And there's my derivative. Isn't that cool? And notice that the derivative, does it go from negative to positive? It does. I want to see how this graph looks, the f of x, the original. So so right now I don't see it, but look how big it is. Look how that's 2,000. So it's going to be pretty big. So let's see. I'm going to go 0 to, let's try 3,000 first. Nope, it needs 5,000. And okay, I need to mess with my x. 0. Oh, okay. I got these x as a y confused. 0 to 10, and 0 to 5,000. That one, 5,000. Here we go. Yeah. You know what? I want to see a little bit past the x-axis here, like below the x-axis. Oh, there's a fly. Negative 100. No, let's go negative 1,000. And I'm going to go a little bit to the left. Negative 3. Don't pay attention to these curves to the left of the y-axis, because remember, we're talking about the radius. So the red curve is my area. Do you guys see that? The blue curve here is a derivative. And you can tell, look how it's going up. So I definitely have a minimum. So there it is at 5.41926. Let's see if this grabs that minimum. Look, there it is. It grabs it. It doesn't grab it as nice as the derivative one, but it grabs it. Cool, right? So there, and oh, okay, check it out. Look at that concavity. What's the concavity of that graph? Up. So at that critical point, your concavity is concave up, so that's how you know there is a minimum. So that's one way that, and you know what? I did talk about it, so let's mention that. So if you wanted to say this is a minimum with the second derivative test, here's how you would do it. You would go a prime prime equals, and we take another derivative. I'm taking the derivative of this guy right here. 4 pi plus 2,000 times 2 is 4,000. R to the negative 3. So let's rewrite this. 4 pi plus 4,000 over r cubed. And look, check it out. This is always positive because r is always positive. And you can say this. You can go, let's see, what dimensional is the least material? Okay. So the radius required for the least material is r equals 5.41926. Well, actually, I should be putting approximate, but that's fine. Which is the cube root of 500 over pi. We know this. We know this is a minimum since a prime of 5.41926 is 0, and a prime prime at 5.41. I'll write this in the next line because I can't fit it right there. And a prime prime of 5.41926 is positive. Hence, r equals 5.41926. 41926 must be a min for area. On concave up, that critical point is 0. That critical point must be a minimum. Does that make sense, guys?
I have a question.
Yeah, what's up?
Why or how do we know that radius is always positive, or
We
is
can't-
always more than 0? Isn't greater than 0?
We can't have negative distance. Like we can't have. These are real values. You're designing a can,
Okay.
so you can't have a negative
Radius.
r value. Yeah, you know what I mean.
Also, because when you put in 0 for the radius, when you get undefined.
Zero itself will be undefined for my derivative and for my area as well, right? But you can't have negative values because you can't, like, when you measure a radius, it has to be a positive value. That makes sense? I hope I didn't say it like too shady or whatever. You could have used the first derivative, negative, positive, as we showed with Desmos. I like Desmos, guys. It's pretty cool. You can actually tell it to give you the second derivative also. So this one, the second derivative would always just be negative because, always just be positive because it's concave up. So if we were to put f prime prime here, it would just show above the x-axis. F prime prime. See? It's always above the x-axis. It never goes below. All right. Cool or not cool? Okay, now let's go to more traditional problems. Maybe you liked that problem. Maybe you didn't. I don't know. Before we do this example 5, because that's the hardest one, let's go to example 6. You guys okay? You don't have your you don't have yours? Oh, you don't have yours?
Oh no, I think it's finished writing it.
Oh, okay. Sorry, miss. Oh, sorry, miss.
Can I put this in your fridge?
Yeah. There. I put it back. I also record it so you can always go back to it.
Is it on?
Yeah, it is on, but sometimes they leave the door closed or slightly open so it doesn't get cold. Is it closed? Is it closed?
Yeah, it was
Okay.
closed.
Yeah.
It was closed.
Okay. There, I just heard it turn on.
Oh, okay.
Yeah. Let's go to this example. Don't worry, guys. We're almost done. This is a traditional question. Common question.
Sorry.
No, that was for traditional common. Yeah. I don't know how to talk, miss. I told you I don't know how to speak English or Spanish. You're good. Well, if it comes out every time, is it traditional? Okay, I'll stop. A rectangular playground is to be fenced off and divided into 2 parts by a fence parallel to one side of the playground. 240 feet of fencing, so there's my restriction. 204, I'll put the word restriction for that. Restriction is used. Find the dimensions of the playground that will enclose the greatest total area. So there it is, underline greatest total area. That's what they want to maximize. So I'm going to draw a rectangle. And it doesn't matter how we partition it. It's part of the fence, part of the fencing. Do you want to partition it vertically or horizontally? Like that? Or do you want me to partition it like that? Oh, okay. Like this. Okay. So usually I use horizontal displacement as X and vertical displacement as Y. You do not have to use X and Y. You can use any letter, length and width if you want. And then, so look how much fencing I have. So I know, so that's X, this is Y, this is Y. The vertical displacement is Y. So I know that 2X plus, how many Y's do you have? 3 Y's better equal how much? 240. We're going to use, well, less than equal to really, but I just put equal to. All right. Now next, what is the area of that rectangle? What's the area of that rectangle? Yeah. X times Y, Y times X. Don't worry about the partition. What's the biggest area that I can get on this whole thing? You know, I guess you can say x times y here, and then whatever. Like it's this x times this y will give me all of that.
Would it be 2xy?
No, because I don't have twice the x. See, 1x, 1y will give me all of that. You see it? Okay. So this is what I want to maximize. So this is what I'm going to take a derivative of. Do you guys see that? And yawning, that's the mirror. So here you go, guys. Take this expression and solve for y so you can get everything in terms of x. So we're going to write 3y equals 240 minus 2x. Divide everything by 3. Divide by 3. Divide by 3. Divide by 3. Y equals 3 goes in 24 8 times. So 80 minus 2/3 x. What's up?
Could we also solve for x?
Yes.
Okay.
You could have also solved for x, get it in terms of y, and plugged it in and just take the derivative with respect to y. Are we still okay, guys? All right, here we go. Area equals x, parenthesis, instead of y, I'm going to plug in this. 80 minus 2/3 x, close. I'm just going to distribute. There's no reason to do the product rule. 80x minus 2/3 x squared. Are we still okay? All right, here we go. I'm going to take a derivative. That's what I want to maximize. What's the derivative of 80x? 80 minus, what's the derivative of 2/3 x squared? Yep. Equal that to 0. I can already see. Yeah, that's the second yawn there. All right. This is a linear line. So I hope that you can see it. My y-intercept's 80, and I have a negative slope. So whenever I find that critical point, my derivative is going from positive to negative. But it's a linear line just going like that. Do you guys see that? So whenever I find that x value, that's my max. See? So these, whenever it comes to something like this, it's usually pretty straightforward. You're going to see that every time you find the critical number, it's usually the number you want. But make sure you understand why, because my derivative is going from positive to negative. Cool or not cool? All right, here we go. 80 equals 4/3 x. I'm going to multiply by the reciprocal because I moved this to the right. See? So times 3/4. Whatever you do to one side, you do to the other. So let's see what we get. 4 goes into 8 2 times. So this is 3 times 20 equals x. So 60 equals x. Are we still okay? All right, now that I got that x is 60, I can figure out the y value. And I'm just going to plug it in right here. Y equals 80 minus 2/3 times 60. So let's see, 80 minus 3 goes into 60 20 times. And 20 times 2 is 40. 80 minus 40 is 40. So there it is. Y equals 40. So what gives me the biggest area? 60 by 40. And these are in feet. 60 feet by 40 feet. Cool or not cool? Yeah, there it is. C. With a 40 feet divider. Yeah. You know what I just remembered, guys? We found the radius of the cylinder, but we didn't find the height. How come you guys didn't tell me? It's fine. The relationship is, remember we had the relationship, the restriction.
Oh, yeah, they did ask us for dimensions.
Yeah. Yeah, real quick. Should we go back really fast? All right. Let's put it in really fast. Here is my equation for my height. We already found the R. I still have it saved in the calculator as R. So height equals 1,000 over. Okay, here's a common mistake. 5.41926 close it squared. Common mistake that you guys do. Here's my calculator. You guys will do this. 1,000. Nope. That too, but 1,000 divided by, and then you'll go pi that squared. Okay, so I still have it as R. So look. Pi alpha r squared. Did I do it right? No. You did not do it right. The calculator is dumb. It's just a machine. The calculator thinks you're doing 1,000 divided by pi, whatever that is, times r squared. So either use parentheses all the time, or to never mess up, never, make it a habit, even if it's something minuscule, to never mess up, use alpha, y equals, enter, and then you'll never mess up because there has a numerator and a denominator. You're forced to put something at the top. You're forced to put something at the bottom. Does that make sense? So there it is. So now we'll never mess up. So 1,000 up here. And pi, was it pi r squared? Pi, was that my equation for height? So there it is, 10.838. So we can have good notes. H equals 10.838. And then I need units, centimeters. So I'll put it right here. Dimensions are height equals 10.838 centimeters with a radius of 5.41926 centimeters. There we go. And that would minimize the surface area. Sorry that I had to do that. That's a third yawn, miss. I'm keeping track. Okay. What's a weird word? Oh. 15 seconds.
No.
I'm not counting. Okay, last question, guys. This one is the hardest one. We're going to do a hack. And when you take this one on Delta Math, this one comes out on Delta Math a lot, level 2. They give you quadratics and all that good stuff. Guys, use your calculator and use Desmos, and you'll be fine. Use your calculator. So check it out. So it says, find the coordinates of the point on the curve. So y equals square root of x plus 4 that are closest to the point 7, 0. You guys are visual, so let's do the visual so you guys understand what's going on. Here's a grid. That square root of x plus 4 looks something like this. Here's negative 4. It looks like, and it goes on forever like this. This point is something like, I don't know, like right here. So I'm going to put like right there. So there's my point, 7, 0. And what they want to know the point on this curve that is closest to this coordinate 7, 0. So they want to know, is it this coordinate? Is it this segment that's the closest? I'm going to call that D. Is it this one? D. And no yawning. Is it that one? That's D. Hey, no, you can't stop because we won't stop. You say okay. Just accept it. All right. Which point is it on the curve? I guess what point am I talking about? This one right here in blue. I mean in purple. And there's an infinite amount. It keeps on going. Just put in there infinite amount. Which line? All these are possible candidates. All those points on this curve are possible candidates for closest to the point 7, 0. Yeah. Because you won't stop. All right. Ready? I don't even know what to say now, you know. All right, here we go. Do you guys remember the distance formula?
Yes.
What is it?
Y2 over Y1.
What? Y2 over Y1? I've never heard of that.
Y2 over X2.
No. Okay.
Oh, Y2
Pythagorean theorem.
Oh, no.
Oh, yeah, Y2 minus, yeah.
Y2 minus Y1 over X2.
No. Okay, guys. Man, what? All right, let's talk about geometry for a little bit. Okay. Yeah, let's not write this down. Just listen. So, do you guys see how I can make a right triangle here for all and make these hypotenuse and make the D there a hypotenuse? I can call that A. I can call that B, and I guess I can call that C. And I can just say that's A squared plus B squared equals C squared, right? And then from there, you're supposed to make a connection between that and the distance formula in geometry. And the distance formula that they show you when you're in geometry is the square root of the change in x squared plus the change in y squared. You guys remember that?
Oh, yeah.
This is Pythagorean theorem in disguise, guys. They're brothers and sisters. Look, if I call the change in x A, and I call the change in y b, and I call the d here a c, then look, you got a squared plus b squared equals c squared, which is the Pythagorean theorem. And then when you take the square root of that, well, whatever you do to one side, you do to the other. Oh, c equals the square root of a squared plus b squared. OMG, look, this looks exactly the same. Pythagorean theorem and distance formula are the same, guys, and that should have taken like a week of exploration for you to figure that out on geometry, but we just did it in a few seconds. Do you guys remember all that? Okay, so there we go. They're related, guys. They're the same. Distance formula and Pythagorean theorem are brother and sister. One of them's called Tyrese, and the other one's called Tigress. Oh, I like that. Tyrese and Tigress. Okay. All right. So here it is. There's the distance formula. You guys ready? So I got two coordinates. I got the coordinate 7, 0, and I got the coordinate on this curve. And since I don't know what x value it is, I just put x, comma, and I don't know what y value it is, but you're going to put it in terms of x. Well, look what I have here. My y value in terms of x is what? Square root of x plus 4. No, you're so smart. So do you guys see what we're doing?
Yes.
So now when I come over here, okay, go ahead.
Why are we just defining that specific point?
Yeah, you can see that. Any of these points could be that.
Okay.
And because that's why there's an infinite amount. So that point is any point on that curve. Yeah. I didn't get slapped by that wire. Yeah, they saw me get slapped. I got hit, but okay. All right, here we go. I'm not embarrassed, guys. No, we're fine. That coordinate is 7, 0. All I'm doing is changing x and changing y. That's all I'm doing. So changing x, 7 minus x, close it squared, plus, and then changing y. 0 minus square root of x plus 4, close it squared. Are we still okay? What happened? What else?
Oh, nothing. Oh.
Yeah, we're about to show you a hack though. Guys, what makes this really hard is the chain rule. It's the square root. Do you guys see that? And I actually, I like what Delta Math did on this. So here's what Delta Math did, and I didn't take the joke from them, but did you do these problems? Yeah, see, so square that, and then they just say, this is what we're going to try to minimize. So they just call that the new function. So they go like, look, squared. So here's your Pythagorean theorem. D squared equals 7 minus x, close it squared, plus 0 minus square root of x plus 4, close it squared. And then they just say, well, what does it matter if I have a square root or not? This is what I want to minimize. I'm going to call that f, and I'm going to take the derivative of that. Does that make sense? Delta does this. They put and I don't have Delta's habits, so I don't do it. They call this my new function f, and then they go f prime. I'm not going to do that. I'm just going to leave it like this, and I'm going to say, okay, I don't care about this. So I'm going to say, don't care. So I'm just going to rewrite it. I don't care about it, guys. Oh, put the word hack. Let's try to understand the hack before we use it. Okay. Don't worry, I'm not going to get here again. Okay, let's try to understand this hack. What does it matter if you're trying to find the min? Who cares about that square root? It's the expression that matters. So if I try to find the expression, the minimum for this expression, won't that still give me the minimum even with a square root in it? Because I don't understand what you're trying to tell me. If I try to find the optimization, the minimum for this expression, then when I take a square root, it's just going to be a smaller number. Do you see that? Do you see the? So that's the hack. Like, okay, make it easy. I don't care about the square root. Just find the minimum for the expression inside the square root, and that will be the minimum with the square root included. Do you see that? I'll repeat it just in case. Find the minimum for the expression inside the square root. And when I take the square root, it's just going to be smaller anyways. Whatever number you get, when you square root it, it's going to be a smaller number. So if you find the minimum for this expression at the bottom, you found the minimum if it was with the square root included anyways. Does that make sense?
Then why do we have the square root?
Because the distance formula is with the square root. But that's right there. A squared plus b squared plus c squared.
Yes. So all we really need is what's inside the square root.
What's inside the expression inside the square root?
Yeah.
All right, here we go, guys. I'm squaring this. This is easy enough to do by hand. So this is some algebra. So look, we're going to get better at our algebra skills. I'm squaring this. What's 7 times 7? 49. Don't go right to the x. Don't tell me this is 49 minus x squared. It's not. What's 7 times negative x? But you're going to have how many of those? 2. So negative 14x. What's negative x times negative x? There you go. And I'll put it, what I'm doing here on the side. This, what we just did is this. 7 minus x times 7 minus x. See? 7 times 7, 49. 7 times x minus 7x. X times negative 7 minus 7x. Negative x times negative x plus x squared. So you guys can see what's happening. Hey, that's another yawn. One more. I'm going to write one up for sure. All right. Here we go. Plus 0 minus that square root squared. When I square that negative expression, the negative goes away because negative times a negative is a positive, and the square root goes away. Do you guys see that? So plus x plus 4. We're not going to yawn, right? Okay. All right, here we go. D equals, I like to have the biggest x power in the front, so x squared. And then negative 14x plus 1, that's minus 13x. And then 49 plus 4, that is 53. This is the expression I want to minimize. This is what I'm going to take a derivative. D prime equals, what's the derivative of x squared? 2x minus 13 equal this to 0. Notice, just like before, I just want you to observe. I want you guys to think that every time you take a derivative, whatever that number is the number that goes over. I have a linear expression. My intercept starts at 13, and I have a slope of 2. So whenever I cross the x-axis, this derivative is changing from negative to positive at the next value. And if the derivative, if d prime changes from negative to positive, that means d has a minimum, or mid. Does that make sense? Okay, hey, miss. We're almost done. 2x equals none. We're gonna break a record of yawns today. Divide by 2. Go to sleep today. X equals 13 over 2. D must have a min at x equals 13 over 2 since this is the only location where D prime is changing from what to what? From negative to positive. Full credit. They wanted the coordinate. Well, there's only one with 13. Don't worry. Okay, let me zoom out. See here. Do that. What? Not on this. All right, I'll stop. I'll stop before Miss Kyle yawns again. All right, here we go, guys. We're almost done. There's only one choice that has an x value of 13 over 2. So the answer is C, but I want to do it the right way. Remember, this is the value on the curve of the square root of x plus 4. Do you guys remember that? And this supposedly that point is the closest one to the 0.70. If I want to find the y value, plug it into the original. So plug what into the original? Y equals this x value. Square root of 13 over 2. What was it? Plus 4? Plus 4. We can do this without a calculator. Hey, no yawning, miss. Yeah, it's contagious, miss. Stop. 13 over 2 plus, I'm going to call this the Yawning Edition. 13 over 2, and then 4 times 2 is 8, so I'm going to write this as 8 over 2. What's 13 plus 8?
21.
Square root of 20, 13, 20. Yeah, 21 over 2. So this is the square root of 21 over the square root of 2. I'm just rationalizing it. Multiply the top and bottom by the square root of 2 over the square root of 2. So 21 times 2. Not at the same time. Double 21? Yeah, 42. There's your y value. Does letter C have square root of 42 over 2? Okay. On Delta Math Part 2, I believe they don't give you multiple choice. You just got to type it in, right? Or no?
No, it's multiple choice.
Oh, or you just type it in? Okay. So there it is. Did they tell you truncated, rounded, or with square roots or whatever, or they come out like they were pretty?
I remember mine in decimals if I had to do decimals.
And they took it.
Oh, I don't know which section. I did all 3 sections. This one reminds me of the last one.
But did this make sense? Like, did this put it all together? Because sometimes I feel like Delta's a little robotic, a little bit, because they just say just blah blah blah. But we're good though, right? Right. So there it is, guys. Tomorrow we will do a circuit, and we're done. Oh, ask me, Miss.
Oh no, can you go back to the part?
Yeah, of course. I can go back to any part.
Thank you. There you go. Wait, a little. Yeah.
No problem. Let me stop recording here.